In this FS5 virtual demo, I'm going to demonstrate how the FS5 can be used to perform a complete photophysical characterization in less than 10 minutes. I have two cuvettes. One is the perovskite quantum dots dissolved in cyclohexane, and the other is the pure cyclohexane solvent. Both cuvettes are placed into the SCO6 cuvette sample module. The first step in any characterization is to measure the absorption spectrum. To do this, I set the desired excitation bandwidth in the signal rate window of Fluorical. I then go to the absorption scan setup, where the desired spectral range is entered. First, the transmission through the solvent-only cuvette is measured. The current excitation wavelength and signal on the transmission detector are shown on the lower status bar. The FS5 is equipped with a transmission detector as standard. The cuvette containing the quantum dots is now moved into position inside the SCO6, and its transmission spectrum now measured. The absorption spectrum is calculated from the difference between the two transmission spectra and is updated live in the software. We now have the absorption spectrum of the quantum dots. The next step is to measure the photoluminescence spectrum. To do this, I go back to the signal rate window and set the desired excitation and emission bandwidths. The sample position is set to 2, which is the position of the quantum dot cuvette inside the SCO6. The emission bandwidth is then increased until I get around 1 million counts per second on the emission detector. In the emission scan setup, the desired scan parameters are then set. The photoluminescence spectrum of the quantum dots is now acquired, showing that they have a narrow bandwidth centered around 525 nanometers. The absorption and photoluminescence spectra can then be combined into one window and normalized in order to more easily compare them. Here, the PL peak and the corresponding decrease in absorbance at the band edge of the quantum dots can clearly be seen. I will now move on to measuring the photoluminescence lifetime of the quantum dots. To do this, I go back to the signal rate window and change the excitation source to the TCSPC laser. The laser is mounted on the front of the FS5, and there's an intensity filter to control the power. Here, I'm adjusting the intensity filter so that the emission count rate is less than 5% of the pulse repetition rate, which in this case is below 50,000 counts per second. Going to tau and then manual brings up the lifetime measurement setup window. The measurement is started and the photoluminescence decay is recorded photon by photon using time-correlated single photon counting. The current progress is shown on the lower left. After the decay has been acquired, it can then be fit to obtain the photoluminescence lifetime. For this sample, I'm using a 4-component exponential model to fit this decay. The fitting shows that the quantum dots have an intensity-weighted average lifetime of 60 nanoseconds. The final characterization is the photoluminescence quantum yield. For this, I switch off the laser and remove both cuvettes from the SCO6. the sample module can then be removed using the quick release button. For quantum yield determination, the SC30 integrating sphere module may be used. The module slides into the FS5 and locks into place. The Fluorical software automatically recognizes that a new module has been installed. For quantum yield measurements, the excitation source is changed back to the xenon lamp and the detector light path is set to the integrating sphere. The solvent is measured first, and the cyclohexane cuvette is placed into the SC30 sample drawer. The excitation and emission wavelengths are both set to the desired excitation wavelength, which in this case is 475 nanometers. The excitation and emission bandwidths are then adjusted to give around 1 million counts per second at the excitation peak. This ensures that the detector will be operating in its linear regime throughout the quantum yield measurements. In the emission scan setup window, the desired scan parameters are entered. For quantum yield measurements, the start wavelength is set to be 10 nanometers lower than the excitation wavelength. The spectrum of the solvent cuvette is now required. The peak at 475 nanometers is the scattered excitation light. Since this cuvette contains only cyclohexane, there are no other peaks present in the spectrum. After the spectrum has been acquired, the solvent cuvette is removed and replaced with a cuvette containing the quantum dots. The emission scan is repeated with the exact same parameters using the rerun button. Again, we have a scattering peak at 475 nanometers, and now also a small photoluminescence emission around 525 nanometers, although it's difficult to see on this scale as the scattering peak is much more intense. The two spectra are combined into one window and the quantum yield analysis wizard is opened. In the wizard, the spectra are now shown on a logarithmic scale, where the emission peak in the sample spectrum can clearly be seen. The wizard automatically assigns the reference and sample spectra and selects the wavelength range of the scattering peak. The wavelength range of the emission peak is then selected using the cursor. The quantum yield of the dots is calculated to be just over 5%. And with that, we are done. A complete photophysical characterization in less than 10 minutes with the FS5 spectrofluorimeter. Thank you for watching.